Hello and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I want to say a little bit more about the rules of transitivity, reflexivity, and symmetry that I introduced in the previous video before we go on in the next one to talk about the substitution of identicals. A couple of things that are worth noting. The rule of reflexivity, you might think, why would we ever just write down that tau equals tau? It's particularly useful in the context where you're doing a reductio ad absurdum sort of proof. So negation elimination and negation introduction, where you assume something and then you're trying to get a contradiction. If you are ever able to prove that some object or some constant or some variable is not self-identical, then reflexivity allows you to write down that it is, and you immediately get your contradiction. So dealing with identity and non-identity, I think it's worthwhile to just make explicit something we defined way back when we were first defining our language, but it's probably worth reminding you of now. So we can talk about identity, for instance, tau 1 equals tau 2, but we can also talk about non-identity. So strictly speaking, the way that you would negate this is an atomic formula. You negate atomic formulas by sticking negations on the front. So it's not the case that tau 1 equals tau 2. However, we will often adopt notation that mathematicians use and just put a slash through the identity. So this is also another way of saying that tau 1 is not identical to tau 2. So these two say the same thing. So I just wanted to say this explicitly so that once I start using this slashed identity symbol notation, you aren't confused about what I mean. The other thing that's worthwhile is noting that if we want to apply the rule of transitivity, order matters. So suppose that I have tau 1 equals tau 2 on line I, and then on line J, I have tau 3 equals tau 2. I can't apply transitivity directly here because it's not something of the form 1 equals 2, 2 equals 3. It doesn't have this very Barbara-like form. Instead, what we would need to do first is at some point, say at line I down here, we would have to apply symmetry to line J. So I've swapped the order of the terms going from tau 3 equals to tau 2 to tau 2 equals tau 3. Now, at the next line, n plus 1, I can apply transitivity to say that tau 1 equals tau 3. So that's transitivity lines I and n. Now you might be sitting here saying, but Dr. Logic, why does it make a difference? Obviously, tau 3 equals tau 2 is the same as tau 2 equals tau 3. Why can't I just do transitivity directly on I to j? This is because things that are obvious to us working in English need to be made explicit when working in a logical proof theory. So yes, it's obvious that these two are the same, but in our proof theory, we've actually defined a rule that tells you you can move from one of these to the other one. And our rules, again, are very sensitive to the particular shape and particular form of the formulas that they are being applied to and that they are deriving. So we know that from these two facts, tau 1 has to equal tau 3. But our proof theory only knows this if we first apply symmetry and then apply transitivity. So these are just a couple of further comments about how these rules work. They really are pretty straightforward and actually not used all that terribly much. What's much more useful and much more important is going to be the substitution of identicals, and that's what we'll talk about next time. Join me then. Until then, take care.